So today we have a target to understand the MOS diode. And this is a little advanced topic. If suppose we go for here and talking about the word MOS, first of all, what exactly the MOS? So this is the metal oxide semiconductor. And we know that FET is being added, then we can say that this is a field effect transistors. So this is a bit advanced topic because we were studying about the diode, and the FET is related with the transistor because we have to go for the BJT bipolar junction transistor. Then we have to come on a MOSFET, means metal oxide semiconductor field effect transistors. The metal oxide semiconductor field effect transistor is composed of a MOS diode and two PN junctions placed immediately. So here we are talking about basically the MOS diode. Adjacent to the MOS diode, since like we are having directly coming on this one, what kind of a structure they have. Let's come up here. So we have a today's target to go for the MOS diode. So MOS metal oxide semiconductor. Here we are going to create a diode. Thus, a MAT, basically MOS diode is a paramount important in the semiconductor device physics because the device is extremely useful in the study of semiconductor surfaces. In practical application, the MOS diode is a heart of the MOSFET, most important device for advanced integrated circuit. The MOS diode can be used as a storage capacitor in integrated circuit, and it forms the basic building block from charge coupled device, CCDs. In this section, we are going to consider the characteristic and else things like that. First of all, let's talk about the ideal MOS diode. A perspective view of the ideal MOS diode is shown in figure 1a. The cross section of the device is shown in figure b. We'll come up here and see that what kind of it looks. If you see this one, this is a simple kind of a substrate. First of all, we go for this B diagram. It's a very simple type of substrate of silicon. This silicon is deposited with the silicon dioxide SiO2, and a surface is being connected like a metal contact, which is maybe taken as the aluminum, and here we have the contact. So such kind of an arrangement, it means a metal, basically a metal is here, semiconductor is here, and oxide is here. So metal oxide semiconductor has such kind of a connectivity. If we view it in a different perspective, we see it looks like this one. So here we have this insulator, here we have this metal, and we have the semiconductor. So that exactly the creation of the MOS diode. So like working throughout the section, it is used to convention that the voltage V is positive when the metal plate is positive biased, and respect to the ohmic contact, V is negative when the metal plate is negative biased with respect to the ohmic contact. So one assumption has been taken with respect to this V and with respect to voltage applied to this one, whether it is positive or the negative. So here we have this diode connection. So here we are going to provide the supply. V may be connected with the positive part, we may be connected with the negative part, both the things are here. So this positive and the negative would have a connected supply here with this metal, and whatever the voltage and potential you are providing to it, that will be appeared here on this metal because it is directly connected with the external supply. This assumption has been taken up here. The energy band gap diagram. So as we are always working with the physics of any device, so here again we have a target to understand energy band gap diagram. So if we talk about the energy band gap diagram of ideal P semiconductor at V equals to 0, first of all, it is no bias situation, but it is not connected with anything. So it is called as a no bias situation. Under this no bias situation, we see here the work function energy. Let's move on to the next diagram and try to understand it, what exactly is being happening. So that is the diagram we are going to discuss about. You see this diagram. So you have here, first of all, talking about this valency, talking about the Fermi energy level, intrinsic layer is there, intermediate layer is there, and we have a conduction. So all of these symbolic notations are being defined here. So let's begin this one and try to understand. So we see here in this section, if we go for this particular energy band gap diagram is here, and whenever we have a simple type of diode, when we have a specifically MOS diode, every time we take care about this energy band gap diagram. So here in this section, let's talk about what exactly the energy band gap diagram represents. So energy band gap diagram of an ideal p-type semiconductor MOS at V equals to 0. So what kind of energy band gap diagram has been taken? It is for the ideal p-type semiconductor MOS. The work function is energy difference between the Fermi energy level and the vacuum level. Here, if you see here, that is Q phi m for the metal and Q phi s for the semiconductor. That's very important. So here we have just taken this Q phi m and talking about Q phi s. So as we have here what? The metal, and what we have here? We have a semiconductor. And metal and the semiconductor all are fixed. So that's why it is being taken at the vacuum level. Level is to be called as a vacuum level at which basically all kind of phenomena may persist. It means we feel that it will become completely free and will have no obstructions. When it has no obstruction, that will be called as a vacuum. So if you read up here, you would be able to get the work function is the energy difference between the Fermi level and the vacuum level, which is taken as a quantum state for the metal and Q phi s for the semiconductor. Also shown the electron affinity is to be taken as a Q psi, which is the energy difference between the conduction band H and the vacuum level in the semiconductor H as Q psi b. So which is the energy difference between the Fermi energy EF and intrinsic Fermi level EF. So all representation has been taken up here. So important, we have a metal connectivity. Here, if you see in between that, we have oxide, the same is there. So we have oxide label. Here we have a semiconductor material, and specifically what kind of a semiconductor we have taken, which is the P-type semiconductor. P-type semiconductor is now connected with the valency as well as the conduction. So that's all representation. Q phi m talking about Q phi s, Q psi, Q phi b. So all these Eg by 2. So xi and psi. This is xi and this is psi. So this all has been taken to just represent all these quantum state. All the energy differences are here. So that has been taken. So not in a specific, but in a big sense, we understand that this is just only representing that to make it in a free state. To free state, what kind of energy and work function requires to go. So this is exactly the condition when we have V equals to 0 state. So that we have already studied up here. Moving ahead. An ideal MOS is defined as follows. A zero applied bias. The energy difference between the metal work function is Q phi m and the semiconductor work function Q phi s is 0. It means like work function is related with, it means if suppose it need to be become conducting, it need to become free in which it has no obstruction. So what is the amount of energy is required? This is the work function. What is the amount of energy required? This is the work function. So this is simply saying that if suppose you have a simple MOS and this MOS diode has certain kind of energy band gap diagram, under that band gap diagram, you have to talk about the work function. This work function is everywhere. In the PN junction, it has a work function everywhere specifically. But here in this work function, it has a significance that how much amount of that energy and the power difference is required. So they are doing nothing but simplifying that equation. So what they have just taken, so the work function difference in what metal and semiconductor, that is taken as Q phi ms. That has been taken as a Q phi ms. So that can be taken as Q phi m minus Q phi s. So that is equals to taking some equations, which is giving some all the sum of energies. If you see here, nothing but this energy, this gap of energy, this gap of energy, all sort of this energy gaps has been given up here. So making this equation and creating this one. So this gives you the work function of difference, where the sum of three items in the bracket equal to the Q phi s. In other words, the energy band is flat band condition when there is no applied voltage. So this is a very simple equation. Having a linear equations are here. So when there is no voltage applied, so this is almost equal to each other. This is a balancing situation. It means they are equal to each other and becomes equal. It means the difference is nothing. This is exactly the meaning of zero bias. The only charges that exist in the diode under the biasing condition are those in the semiconductor and those with the equal but opposite sign in the metal surface. They are saying simply at that time, suppose you're providing a certain voltage here, and in that situation, it might be possible it may start conducting. But before that, when you are not providing any voltage, V equals to zero. So it might be possible some of the charge may be here on metal, some of the charge may be in the semiconductor. So it might have its own charge storage that they are talking at the V0. So there is no carrier. So the only charges that exist in the diode, I'm repeating this one. See, understand it very carefully. The only charges that exist in the diode under any biasing condition are those in semiconductor and those with equal but opposite sign on the metal surface adjacent to the oxide. As we have this semiconductor, as we have this metal, the semiconductor has some charges, this metal has some charges, and in between that we have SiO2 layer. Okay, so there is no carrier transport phenomenon, transport through the oxide under the current current biting situation, because we are not providing any voltage, or the resistivity of the oxide is infinite because it is not allowing to movement of any charge from semiconductor to metal and metal to semiconductor. So that's why we say at this time the silicon dioxide has a wide phenomena of infinite resistance, because it is not allowing, where there is no current, it means we can say infinite resistance. It's like that. This ideal MOS diode theory serves as a foundation for understanding practical MOS. So first of all, we have just taken this ideal theory. When an ideal MOS diode is biased, now coming on this point, with positive or negative voltage. So we have a V terminal here. So that is, you see here, we have this V terminal, and this V terminal can be connected with the positive voltage, can be connected with the negative voltage. So taken up here the same case. So when an ideal MOS diode is biased with positive or negative voltages, three cases may exist at the semiconductor surface. For the case of p-type semiconductor, when a negative voltage is applied to the metal plate, excess positive carriers will be induced at the SiO2 Si interface. So what we are doing, what kind of a voltage we are providing when we are providing a negative to this one. So here you are providing negative. Here you have P type of semiconductor, so the holes will be attracted towards it. And in between that, what we have? SiO2 layer. So at the SiO2 layer, because they cannot just cross on this SiO2 layer, so there will be a deposition. There will be a deposition at the surface of SiO2 and the Si. So that happens. In this case, the band near the semiconductor surface are bent upward. In this case, the band near the semiconductor, you see here, like that situation, that bending. It means because the holes are reaching up here and they are having a increasing of their energy. So while they are increasing up their energy, so obviously those are reaching near to the SiO2 will have a more energy as compared to others. So that exactly shown up here. For an ideal MOS diode, no current flows in the device regardless of the value of the applied voltage. Thus, Fermi level in the semiconductor will remain constant. Previously, we determined the carrier density in the semiconductor depends exponentially. This is the very common formula we have already talked about, that intermediate state Fermi energy level depending upon the K by T. Intrinsic semiconductor concentration is here and the PPA is here. So this is all about, this is exactly the all about the carrier concentration finding out formula related with the semiconductor. This is a very known formula that we have taken up. Important point, for an ideal MOS diode, no current flows in the device regardless of the value of the applied voltage. Thus the Fermi level of the semiconductor will remain constant. Why the current will not be flowing in the ideal diode? Because we say We are having a metal contact, we are having a semiconductor. Deposition of the charge carriers may be there, but in between that we have a silicon dioxide, and that silicon dioxide is working like an insulator. It is not allowing any flow of current like this, because in between the semiconductor. That's why it is being told that in ideal condition, whatever the voltage you will apply on this metal terminal, there will be no flow of current through SiO, ideally. The upward bending of the energy band at the semiconductor surface causes an increase in the energy EIEF there, which in turn give rise an enhanced concentration and accumulation of hole near the oxide semiconductor interface. This is called accumulation case. The corresponding charge distribution is shown in figure 3. We will see that. Important. So the upward bending of energy band gap we are talking about semiconductor surface causes an increase in the energy EIEF, which in turn give rise to enhanced concentration and accumulation of hole near the oxide semiconductor interface. This is called accumulation. You see here, we can get this. So here, if you see this EC is rising up a little, EV is rising up a little, this bending is taken place, and this difference, if you see here, this Fermi energy level difference and EI, which is intermediate Fermi level, will be increased. So this is exactly the case being discussed up here. See, this is the very first case when we are applying a negative bias voltage here. So this is a very good case under the case of the V less than 0. Here we're having this Fermi energy level, and this kind of a situation has happened. I'm just opening this session for your questions. You have such kind of a structure. And what is the option you have? You are connecting this particular substrate with the ground. So you have two options. Not basically the two options, I must say 3 options you have. Either you are not connecting anything you are not connecting. Then you can say, I have a case of V equals to 0, no bias. Second case, you may connect V equals to positive voltage. In the third case, you can connect V equals to negative. Remember, here we have this metal, here we have semiconductor, in between we have a silicon dioxide, which is insulator, absolutely insulator. So what is happening when you apply the voltage here? This is a kind of a dielectric material. It is not allowing to movement of any charge carrier, but whatever the voltage you give at this terminal, that will be appeared on the second surface of silicon dioxide. This is because of the polarization effect. This is because of the dielectric effect. So this dielectric effect will be here. Suppose you're providing negative voltage. So this negative voltage will be appeared here because electric field will be set up. And once the electric field will be set up, so here the negative potential will be appeared. And this negative potential will be attracting all the holes of silicon. And then holes starts moving towards the SiO2 layer, and they will be keep deposited. So this is a very phenomenal effect of charge carrier transport. What we have a target? We have a target to understand that during this process, whether it is a zero bias, whether it is a negative bias, whether it is a positive bias, what will be effect of energy band gap? So first of all, you should understand what kind of an energy band gap they have, because we have basically metal, oxide, and semiconductor. This diagram indicates you, exactly tells you that in this particular metal, we have a certain kind of a work function which is represented with Q phi m. We have again a semiconductor material which are having a layers, like conducting layer is there. Here we have a conducting layer, metal has a conduction itself. So this conducting layer is here. We have intermediate Fermi energy level, we have a Fermi energy level, we have a valency band. And we have different sort of energies which represents what will be the difference here. And all of them has been compared with the vacuum level, just only for the purpose of understanding these quantum states. And here we have our oxide. Now the target comes. This is an ideal situation, and ideal situation tells there is a huge gap, and this gap should be balanced. While we are talking about this gap, to maintain this Fermi energy level at the equilibrium state. So if you see here, if the Fermi, because two things can only be created, can only be matched, can only be generated once they are in equilibrium state. So when the equilibrium will come, equilibrium only will come when Fermi energy level will match with each other. So this Fermi energy levels tells you this Q phi s and the Q phi m are equal and opposite to each other. And that's why the difference what we are calculating of Q phi m is 0. There is no work function required. It remains in an ideal state. It remains in an equilibrium state. Suppose there will be a work function, so definitely some phenomena must be keep on going here. If something is not happening, it means we can say it is in equilibrium. If it is something is happening, then some force is more than other. Some effects are more than other. That exactly the point. So got it? So here we talked about, first of all, in this situation, we have zero bias state, and this is called as an equilibrium state. Now the second task, what we are doing, we are connecting this terminal with the negative. When we give this negative, all the negatives will be here, holes will be attracted towards. So this is a physical phenomena, but we are not concerned with the physical. We are also concerned with the energy phenomena. It means quantum phenomena. So what happens here? We see here, this is the flat levels may be converted into the band shape like this one, because once they will be reaching towards this SiO2 layer, near the SiO2 layer, they will be depositing up here. So they will be rising up their energy level, that is shown up here. This banding is done. So we talked about under this negative condition. While we are giving a positive voltage, it might be a second case. We will be giving a positive voltage at this terminal. When we give this positive voltage, positive will be appearing here, and the electrons on the holes, sorry, I'm talking about the holes, will be moving away from the SiO2 layer. And they will be moving away from the SiO2 layer. So once they will be moving from the SiO2 layer, then what happens? This energy band gap diagram will banding while making the lowering of their energy. This state has to be happened. This is exactly the V less than 0 and V greater than 0. And the first diagram we have made, that is V equals to 0. So, well, under my conclusion of today's lecture, we have started talking about the MOS diode. The MOS diode is nothing but a subsection of MOSFETs. It means MOS transistors. Here we are having a simple discussions on a basic physics about the MOS. First of all, because it is made up of metal oxide semiconductor, that's why it is MOS. As it has two electrode, 1 and 2, we call it as a diode. Now, what exactly is happening inside? If we talk about, first of all, construction, the construction includes some metal. That metal may be different depending upon use. So we have metal, we have silicon dioxide as an insulator. Here we have a silicon that may be N type or P type substrate. So it has a certain thickness of T, and this particular has a gradient. So this oxidation process may have a certain, if you go for this one, that oxidation process may have a gradient. It means high to low or low to high or constant. This show uniform. Zero, it means it shows uniform gradient is there, no rate of change. Now we have a target to understand their energy band gap diagram. We have certain energy band gap diagram of metal. We have the certain energy band gap diagram of silicon. Similarly, we have a SiO2 as a gap. We have discussed about basically the gap energy band gap diagram of metal. We have discussed about the energy band gap diagram of silicon while we are connected, and under the situation when voltage is not applied, or zero voltage or zero bias, when a voltage is applied but negative, and the third case when the voltage is applied when it is positive. So in a concluding remark, What happens in a concluding remark? It happens that when we are applying voltage, so there will be effect on conduction band and effect on valency band of semiconductor, as well as there will be effect on Fermi energy level of matter. So that have a changes. Those changes we have discussed in this particular section, and we have covered how this is going to put a change and what kind of a banding and rising and lowering of Fermi energy level being represented, and so that this situation. This is today's lecture. So I'm concluding this one. Thank you.